Okay, this is Unit 3, Chapter 14, Partial Derivatives, Section 14.1, Functions of Several Variables. So in this section, we're going to study functions of two or more variables from 4 points of view: verbally, numerically, algebraically, and visually. So beginning with functions of two variables. The temperature T at a point on the surface of the Earth at any time t depends upon the longitude x and the latitude y of the point. We can think of t being a function of the two variables x and y, or as a function of the ordered pair x, y. We indicate this functional dependence by writing that t is a function of x and y. We also know that the volume of a circular cylinder depends upon its radius and its height h. In fact, we know that v is equal to pi r squared h. We can say that v is a function of r and h, and we could rewrite this as v of r and h equals pi r squared h. So that leads us to this definition, that a function of two variables is a rule that assigns to each ordered pair of real numbers x and y in a set D a unique real number denoted by f of x, y. X and y. The set D is the domain of the function, and its range is the set of the values that f takes on. That is, the domain of f and x, y is such that all x and y are contained within the domain. So we will often write that z equals a function of x, y, to make explicit the value taken on by the function at the general point x and y. So x and y are our independent variables, and z is the dependent variable, similar to what we remember from functions of a single variable. So looking at example 2, so in regions with severe winter weather, the wind chill index is often used to describe the apparent severity of the cold. This index W is a subjective temperature that depends upon the actual temperature, T, and the wind speed, V. So W is a function of T and V, and we can write that W is a function of T and V. So Table 1 records some values of W as compiled by the U.S. National Weather Service and the Meteorological Service of Canada. So we can see that if the temperature, for example, is negative 5 degrees Celsius, and the wind speed is 50 kilometers per hour, then subjectively it would feel as cold as the temperature of about negative 15 without wind. So therefore, f of negative 550 is equal to negative 15. So example 3, so in 1928, Charles Cobb and Paul Douglas published a study in which they modeled the growth of the American economy during the period 1899 to 1922. They considered a simplified view of the economy in which production output is determined by the amount of labor involved and the amount of capital invested. While there are many other factors affecting economic performance, their model proved to be remarkably accurate. The function they used to model was of the form of equation 1, where P is the total production, which is the monetary value of all goods produced in a year. L is the amount of labor, and K is the amount of capital invested. Which is the monetary worth of all machinery, equipment, and buildings. So Cobb and Douglas used some economic data published by the government, and they used that data and obtained table number 2. They took the year 1899 as a baseline, and P, L, and K for 1899 were each assigned a value of 100. The values for the other years were expressed as percentages of the 1899 figures. Cobb and Douglas used the method of least squares to fit the data of Table 2 to the function shown in Equation 2. If we use the model given by the function in Equation 2 to compute the production in years 1910 and 1920, we get that P of 147,208 is equal to 1.01 times 147 to the 0.75 times 208 to the 0.25, which is approximately 161.9. And if we calculate P of 194,407, we end up with approximately 235.8, which are quite close to the actual values as shown in the table. So we're looking at 1910 and 1920, and you can see that we got very close to the actual values of P of 159, whereas we calculated 161, and 231, where we calculated 235. The production function has been subsequently used in many settings, ranging from individual firms to global economics. And this is known as the Cobb-Douglas production function. Its domain is LK, such that L is greater than or equal to 0, and K is greater than 0, because L and K represent capital and labor, and therefore are never going to be negative. Another way of visualizing the behavior of a function of two variables is to consider its graph. So we start with this definition. If f is a function of two variables with domain D, then the graph of f is the set of all points, and this should be in 3 space, such that z is a function of xy, and xy is contained in D. So just as the graph of a function of one variable is a curve with the equation y equals fx, so the graph of a function of two variables is a surface S with the equation z equals f of xy. So we can visualize the graph of S as lying directly above or below its domain in the xy plane, as shown in Figure 5. The function f of xy is equal to ax plus by plus c is called a linear function. And the graph of such a function has the equation z is equal to ax plus by plus c, or ax plus by minus c plus c is equal to 0. We should recognize this as a plane, in much the same way that linear functions of one variable are important in single variable calculus. We will see that linear functions of two variables play a central role in multivariable calculus. So let's look at this example. We're going to sketch the graph of g of xy is the square root of 9 minus x squared minus y squared. So we know that the graph has the equation z is equal to the square root of 9 minus x squared minus y squared. If we square both sides of the equation, we obtain z squared is equal to 9 minus x squared minus y squared, or x squared plus y squared plus z squared is equal to 9, which we recognize as an equation of the sphere with the center at the origin and a radius of 3. But since we know that z must be greater than or equal to 0, we can see that the graph of g is just the top half of this sphere, as shown in Figure 7. So far, we have two methods for visualizing functions: arrow diagrams and graphs. A third method borrowed from map makers is a contour map on which points of constant elevation are joined to form contour curves, or level curves. And that gives rise to this definition. The level curves of a function f of two variables are the curves with equations f of x, y equals k, where k is a constant in the range of f. Therefore, the level curve f of x, y equals k is the set of all points in the domain of f at which f takes on a given value of k. In other words, it shows where the graph of f has a height of k. So we can look at Figure 11 to see the relation between level curves and the horizontal traces that we used in section 12.6. The level curves of f of x, y is equal to k are just the traces of the graph of f in the horizontal plane z equals k projected down onto the xy plane. So if you draw the level curves of a function and visualize them being lifted up to the surface at the indicated height, then you can mentally piece together a picture of the graph. The surface is going to be steep where the level curves are close together, and it's somewhat flatter when they are farther apart. One common example of level curves occurs in topographic maps of mountainous regions, such as the map in Figure 12. The level curves are curves of constant elevation above sea level. If you walk along any one of these contour lines, you neither ascend or descend. Another common example is a temperature function. Here, the level curves are called isothermals and join locations with the same temperature. Figure 13 shows a weather map of the world indicating the average July temperature. The isothermals are the curves that separate the colored bands. In weather maps of atmospheric pressure at a given time as a function of longitude and latitude, the level curves are called isobars and join locations with the same pressure. Surface winds tend to flow from areas of high pressure across the isobars toward areas of low pressure and are the strongest where the isobars are tightly packed. A contour map of worldwide precipitation is shown in Figure 14. Here the level curves are not labeled, but they do separate the colored regions, and the amount of precipitation in each region is indicated in the color key. For some purposes, a contour map is more useful than a graph. It is true in estimating function values. Figure 20 shows some computer-generated level curves together with the corresponding computer-generated graphics. Notice that the level curves in part C crowd together very near the origin. That corresponds to the graph that in Figure D is very steep near the origin. So a function of three variables, f, is a rule that assigns to each ordered triple x, y, and z in a domain D contained in 3 space a unique real number denoted by f of x, y, z. For instance, a temperature at a point on the surface of the Earth depends on the longitude and latitude x and y of the point, but also on time t. So we could write that temperature t is a function of x, y, and t. So looking at example 14, we want to find the domain of f if we are given that the function of x, y, and z is the natural log of z minus y plus xy sine z. Okay, so we know that the function is defined as long as z minus y is greater than 0. So therefore, we know that the domain is the set of all points x, y, and z such contained in 3 space such that z must be greater than y. This is a half space consisting of all of the points that lie above the plane z equals y. So it can be difficult to visualize a function of 3 variables by its graph, since that would lie in a 4-dimensional space. However, we do gain some insight into f by examining its level surfaces, which are the surfaces with the equations f of x, y, z equals k, where k is a constant. If the point xyz moves along a level surface, the value of that function remains fixed. Functions of any number of variables can be considered. A function of n variables is a rule that assigns a number z is equal to f of x1, x2, x3, all the way to xn, to an n-tuple x1, x2, xn of real numbers. And we denote the set by Rn, the set of all such n tuples. So, for example, if a company uses n different ingredients in making a food product, C sub I is the cost per unit of the ith ingredient, and X sub I units of the ith ingredient are used. Then the total cost is a function of the n variables x1 through xn, and we have equation 3. The function f is a real valued function whose domain is a subset of r to the nth. Sometimes we will use vector notation to write functions more compactly. If we define x as x1, x2, x3 to xn, we can often write f of x in place of f of x1, x2, x3. With this equation, we can write the function shown as equation 3 as the function here, where c is going to be defined as c1, c2 to cn, and c dot x denotes the dot product of the vectors c and x in our function. In view of the one-to-one correspondence between these points and their position vectors, we have 3 ways of looking at a function defined on a subset. We can define it as a function of n real variables, x1 to xn, as a function of a single point variable, x1 to xn, or as a function of a single vector variable.